Some materials entirely consist of atoms of a single chemical element. We call these materials elemental substances. The atoms in elemental substances are arranged in specific well-defined ways. This arrangement and the way in which atoms are bound together is different for different families of elements. All metals, except mercury, are solid at room temperature. Atoms in solids are usually arranged on a regular lattice, that is, a grid, and can't move far from their locations on it. Solids where atoms are arranged in this way are called crystalline. Solid metals are usually crystalline solids, although any large piece of metal typically consists of many tiny crystals stuck together. For this reason, metals tend to have considerable plasticity. That is, they can be bent without breaking. The tiny crystals can be moved relative to each other without displacing atoms inside the crystal from their positions on the lattice. We already know that metal atoms do not hold on to their valence electrons very strongly. In a crystal, each metal atom lets go of some or all of its valence electrons. These electrons are then free to fly around anywhere inside the metal crystal, while the remaining cations sit in place. It is said that a metal crystal consists of cations arranged on a regular lattice that are immersed into a sea of electrons freely flying around. Because electrons have electric charge and can move freely, metals tend to be good conductors of electricity. Applying a voltage from an outlet or battery to a metal wire forces the electrons in it to move in one direction, and an electric current is nothing else than such directed movement of electric charges. The total charge of all electrons freely flying around in the metal crystal is the same as the total charge of the cations. If each metal atom in a crystal releases one electron, then for every electron in the crystal there is one cation with a positive charge of the same magnitude. If each metal atom in a crystal releases 2 electrons, then for every 2 electrons in the crystal there is one cation with a positive charge 2+, twice the electron magnitude, and so on. Therefore, metal crystals are overall electrically neutral. Like metals, elemental metalloids are also crystalline solids. However, their atoms hold on to valence electrons more strongly than the atoms of metals. Rather than letting go of these electrons completely and letting them fly around throughout the crystal, metalloid atoms share their electrons only with specific atoms next to them. A bond formed when 2 atoms share one valence electron each with each other is called a covalent single bond. In such a bond, 2 electrons, one from each of the 2 atoms, tend to be in the region between these atoms. Because the electrons that form the covalent bond stay close to their atoms and can't move around the crystal freely, metalloids do not conduct electricity as well as metals. Covalent bonds are strong and allow metalloid atoms to form very large crystals, rather than the multiple tiny crystals stuck together that are typical of metals. Such crystals are brittle. They tend to break rather than bend. Some nonmetals, most notably carbon, also form crystalline solids with covalent bonds between atoms. Diamond is a crystal that consists of carbon atoms connected by covalent single bonds. These covalent bonds are responsible for diamond's hardness. Elemental nonmetals can also form molecules that consist of a well-defined number of atoms of the nonmetal with a well-defined arrangement of these atoms. The atoms in molecules form covalent bonds with each other. Molecules of elemental substances are by definition homoatomic, that is, they consist of only one type of atoms. In some cases, two covalently bound atoms may contribute more than one electron each to the bond. If each atom contributes 2 electrons, for a total of 4 shared electrons, the bond is called a covalent double bond. For instance, 2 oxygen atoms connected by a covalent double bond form an oxygen molecule. If each atom contributes 3 electrons, for a total of 6 shared electrons, the bond is called a covalent triple bond. For instance, 2 nitrogen atoms connected by a covalent triple bond form a nitrogen molecule. The oxygen and nitrogen molecules are diatomic, that is, they consist of 2 atoms. The halogens also form diatomic molecules with covalent bonds between the atoms. However, some nonmetals form molecules that consist of more than 2 atoms. Such molecules are called polyatomic. The Greek prefix poly means many. For example, white phosphorus is made of molecules that consist of 4 phosphorus atoms each, arranged into a triangular pyramid. The most common type of a sulfur molecule consists of 8 sulfur atoms that are arranged into a crown shape. In these pictures, the balls represent individual atoms, and the sticks between them covalent bonds. At room temperature, molecules may come together to form solids like white phosphorus or liquids like molecular bromine. When they do, the interactions between different molecules in the solid or liquid are not chemical bonds. They do not involve the transfer of electrons from atoms of one molecule to atoms of another, or the sharing of electrons between atoms of 2 different molecules. Molecules may also fly around throughout all space that is made available to them, forming a gas. When molecules form a solid, it may be a crystal, where molecules are arranged on a lattice to form a regular pattern, just like atoms are in atomic crystals. However, the shape of molecules, particularly of larger molecules that consist of a relatively large number of atoms, is more complex than the shape of atoms. Therefore, oftentimes, it is more difficult for molecules to arrange neatly on a lattice to fit together. Instead, they clump together with little order. Solids with such an arrangement are called amorphous. Atoms of many elements, such as carbon and even some metals like iron, can also come together to form amorphous solids. But generally, atomic solids have a higher propensity for being crystalline. For many elements, multiple arrangements of atoms relative to one another is possible. This is true of both crystalline and molecular substances. Elemental substances that are made of atoms of the same element but have different arrangements of these atoms are called allotropes or allotropic forms. The arrangement that atoms prefer to assume is determined by pressure and temperature, but sometimes 2 or more types of atomic arrangements at the same pressure and/or temperature are possible. More than half of metals can form more than one crystalline allotropic form at atmospheric pressure. For example, here are 2 possible arrangements of atoms in iron, so-called alpha phase and gamma phase iron. Iron is a metal, so the lines connecting atoms are not covalent bonds, they are just shown to make discerning differences in the relative arrangement of atoms easier. Molecular substances also commonly have multiple allotropes. For instance, whereas the most common allotrope of sulfur is a molecule that consists of 8 sulfur atoms in a crown-like shape, Other allotropes, such as a molecule that consists of 6 sulfur atoms forming a ring, are also known. Different allotropes of the same element can have very different appearance and other properties. For example, here are the images of white phosphorus, red phosphorus, and black phosphorus. 3 allotropes of phosphorus. All 3 entirely consist of phosphorus atoms, but have different colors because of how the atoms are arranged. Carbon is the element that is known for a particularly large variety of allotropic forms. About 500 are known today. Common crystalline solid forms of carbon are diamond and graphite, the gray substance that is used in pencils. Both consist entirely of carbon atoms. Carbon atoms can also form an amorphous solid. In addition, they can arrange themselves to form a multitude of molecules. A well-known carbon allotrope is a Buckminster fullerene or buckyball, a large molecule that is made up of 60 carbon atoms arranged in the shape of a soccer ball. Other polyhedron-shaped fullerenes with different numbers of carbon atoms in the molecule also exist, as well as large carbon molecules of other shapes.